So whenever I play the mass spring oscillator and the pendulum at the same time and plot their velocity versus time graphs, I get what I expect. I did make it so that these guys have pretty much the same period, not exactly, but pretty close to the same period. And notice the one period of a mass spring oscillator is the time it takes to go back and forth to the original position, moving in the same direction, right? The pendulum, one full period is the time it takes to go to the other side and then back, okay? And then if I plot velocity versus time, I get that kind of stuff. Note that if I were to, and I pointed this out in the beginning, because we now know that the equation for the period of a pendulum is 2 pi times the square root of L over G. And I have pointed out that anytime you see pi in an equation, there's a circle there somewhere. It might not be a physical circle in physical reality, but it's hidden in the mathematics somewhere. And so if you plot the right things, like say velocity in the x direction versus position in the x direction, and then I hit play, then I can get a circle if I configure my axes. Now it's not a perfect circle, actually, it's more of an ellipse, but pi is involved with ellipses as well. A circle is an ellipse. All circles are ellipses, but not all ellipses are circles. But pi is involved with the mathematical description of all of them. Okay. So that's just giving you a visual on pendulums and how we can graph their motions. Let's dig into it a little more. What's up?
It's exciting.
Exciting, it is. I'm actually going to talk about some exciting things. And for those of you that like mathematics and are planning on being a STEM major, something that you'll learn about in college. So, what did we learn about when we varied the mass of the pendulum? What did we learn about? What did happen when I changed the mass? What happened to the period?
Absolutely nothing.
It didn't change. It didn't change. So the mass does not affect the period of a pendulum. As we'll see when we do an example FRQ today. Does changing the mass affect the period of a pendulum? No, it doesn't. The mass does not affect the period of a pendulum. And then we saw that the length, obviously, the length, and actually I should say this, the period of a pendulum is directly proportional to the square root of the length, right? And that's why you had to do a curve fit. That's why you had to do a linearized graph in order to figure out, what the value, in order to figure out a way that you can figure out the value of G. So not very complicated as long as you understand the process of linearization. What is actually more complicated than you might think is the release angle. And this is the one that I'm not going to scrutinize very heavily because some people might answer it one way, some people might answer it the other way. Their interpretations of the data might be a little different. And that's because the actual effect of release angle on the period of a pendulum, is more complex mathematically than we can actually describe in this class.
Prior to 15 degrees, it has no effect, but after 15 degrees-ish, it has some effect, right?
Up until 15 degrees, right. There's no effect.
Right.
And then bigger than 15 degrees, you end up with an effect. Yeah. So sometime, and it does for angles smaller than 15 degrees, but it's negligible. Okay. And the reason is this. Now, we know at this point, let's say I have a mass spring oscillator where this is the equilibrium position. I can just draw it. And I stretch it. I stretch the spring a distance x, and I get a resulting force. I know that the relationship between the resulting force and the displacement of the spring is given by Hooke's law. And they're always in opposite directions. That's why without the magnitude symbols or the absolute value symbols, there's a negative in front of this term. When I take a pendulum, whose equilibrium position is obviously when it's hanging straight down, and I displace it, I don't say that I displace it a certain distance. You can, but mathematically it's actually much more difficult to deal with that. I actually displace it a certain angle. Okay? And yes, there are forces that, just like with the mass spring oscillator, there is a force. When I take that pendulum and I displace it by a certain angle, there is a force that wants it to get it back to the equilibrium position. But whereas the spring force never changes direction until the object passes equilibrium, the net force on this guy will constantly be changing, right? Because what force do I have? I have the downward weight force and this tension force. But as this guy moves down, mg doesn't change, but the direction of the tension force changes, and the magnitude of the tension force changes. It gets larger as the pendulum sweeps down. So it's much more complicated to talk about the restoring force on a pendulum. What's much less complicated is talking about the restoring blank on the pendulum, where blank is not just the force, but the force that is trying to get the system to rotate, right? A pendulum essentially rotates, right? We could say it's kind of weird to think of a single mass that's rotating as it's moving, but if you take a physical pendulum, whose physics is almost, if you take physics C next year, you'll see is almost identical to a pendulum's motion, right? I have this object, and it's rotating, right? It's rotating as it swings back and forth. There's equilibrium. I displace it from equilibrium, and then I get not a restoring force, I get a restoring force that causes rotation. Does anyone know what we call a force that causes rotation? Torque. It's a torque. So I get a restoring torque. Okay. So here, with the mass spring oscillator, I get a restoring force. Force is easy. Force is real simple. It's just how many newtons are you pushing or pulling with. Torque is more complicated. And torque is actually going to be one of the central themes to our next unit, which is rotation, which will be your favorite unit by far. Okay. You get a restoring torque. Torques cause rotation. They are more complicated because they are due not only to the force, they're also due to the distance from the application of the force to the fulcrum, or the axis of rotation, and they're also due to the angle between those two, right? So the force is one thing, a torque is due to three things, and their relationships between each other. And what I can say is that the torque is directly proportional to not the angle, but the sine of the angle for a pendulum. And to see why that's the case, let me draw a quick free body diagram. I got mg. Let me put it on this side. And then I got a tension force. Well, if I decompose mg into a component that is parallel to the string, and then anti-parallel or perpendicular to the string, I know that this guy, and notice that this angle here is congruent to that one, right? The angle I make here. So this is the adjacent side. This is mg cosine theta. This is mg sine theta. The cosine component doesn't cause rotation. It's just trying to pull away from the tension force. Right? There's no rotation caused by that component. There is rotation caused by the sine component. So that's why with a pendulum, if we're measuring the angle with respect to the vertical, the torque is proportional to the sine of the angle. Here's what's interesting, and for future engineers, future physicists, this is actually important in a lot of different applications. For small angles, the sine of an angle theta is approximately equal to theta itself. That's called the small angle approximation. There's other things that you can delineate from the small angle approximation. This is only if you're dealing with radians. This will not work for degrees. But if you're dealing with radians, small angles, you can just say that theta is the sine of an angle is approximately equal to the angle itself. If you don't believe me, get out your calculator. Do the sine of 0.1 radians, and then it'll be about 0.1. Okay. Graphically, for those of you that can graph sine y equals sine x, we can see why this is true. And pretend we're in our math class, so we are graphing y equals sine x. And if I graph y equals the sine of x, I know it's a graph that looks like this. And it just goes on forever. It's wavy like that forever. But what if I were to graph y equals x? We all know what that looks like.
Oh, yeah, that's cool.
That's this guy. Right? And so for small angles, we're talking about values that are close to the y-axis. X values that are close to the y-axis. If we have x values close to the y-axis, those are pretty much right on top of each other. So for small angles, the sine of an angle is just like the angle, and then what that tells us is that the restoring torque is just like a restoring force, because it's not proportional to the sine of something, it's just directly proportional to that thing.
Whereabout is the cutoff of radians?
The cutoff is however many radians 15 degrees is. About 15 degrees is where, beyond that, the approximation is not valid, because now you're going to start getting into that deviation territory. Okay. So that's why I'll know, and that's why I'll be very forgiving when I grade that part of the lab, based on your answers, because for small angles, yeah, it doesn't affect it, and this is true. For larger angles, this equation actually is not true, right? It doesn't work. Now I want to point something else out, because there's, I've told you this before. When I was in high school, I didn't take physics, I didn't take calculus, I stopped at pre-cal. I was not a very good student, and when I got to college, I was hit hard. I was hit hard by the stuff that I really want. I love science, but I just wasn't into it in high school. When I got to college, I was hit hard, and so what I'm going to show you is why I'm going to give you a little more insight into why the small angle approximation actually works, because it's also historically interesting. Because guess what? Before the 1940s, people didn't have calculators. People couldn't just say, I wonder what my theoretical work here, or my engineering project that I'm working on, requires me to know what the sine of an angle is. How do they know what the sine of the angle was before a calculator?
Do the math.
What does do the math mean, though? How do you figure out what the sine of an angle is in the 1600s, right, before electricity? What's that?
You have to do it yourself.
What kind of calculation?
I remember we learned about it, because there's a way to do it without a calculator, right?
Well, yeah, but you probably haven't learned about it yet.
I remember talking about it, just
You could do a simple ratio.
We didn't
I think that's what Jacob was talking about. You could do a simple ratio. But the thing is that notice how y equals x for small angles is a pretty good approximation of y equals sine x. Well, I can actually add another term. I could say y equals x plus some x to the third power, plus some coefficient times x to the third power, and then this line will start to curve, right? And start to mimic sine x. And then I can keep adding terms. I can keep adding terms, and each subsequent term will get this to more closely match sine x, right? And the process of doing that involves derivatives, which some of you guys know about, and doing an iterative process where you do a bunch of derivatives and figure out a bunch of new terms, and then you just add them all together, an infinite number, in fact, and then you just add them all together and you get an equation that's essentially a polynomial that mimics exactly y equals sine x. Not only did they do this for sine x, they have done this for cosine x, for tangent x, for e to the x power, right, for the natural log of x, all of those different types of graphs. You could get values for, what? Oh, thank you. Again, you don't need to do this in this class, but this is one of the things that I struggled with, because I got through first semester calculus in college pretty well, but struggled through second semester calculus. The process of going from y equals sine x to an approximation that I can actually just calculate by hand is called a Taylor series. And when you do a Taylor series expansion about the equation y equals sine x, you determine that the sine of x, and I'll use theta since we're dealing with the angles in theta, using theta as the variable. Sine of x can be written like this. The infinite sum, so the sum from k equals 0 to infinity, of -1 to the k power, meaning that each term is just going to alternate between positive and negative, right? When k is 0, it's -1. When k is 1, when k is 0, -1 to the 0 power. What's -1 to the 0 power? It's 1.
It's just one.
Yeah, it's just 1. I'm sorry. Brain fart. Over 2k plus 1 factorial. Have you guys learned about factorial yet? Factorial, just if I have 7 factorial, it's just 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. Right. And then multiplied by theta to the 2k plus 1 power. That is, if I want to know it, this is literally the same thing as sine of theta, right? Before you had a calculator, and let's say you didn't have a triangle that you could just measure the ratios of to see what the angle was, the sine of the angle was. And even if you did that, you would just know the sine of the angle. You wouldn't know the angle itself, unless you measure it. What this ends up being, though, when you actually work it out, is just theta minus theta cubed over 3 factorial. That's the second term. Plus theta to the 5th power over 5 factorial minus theta to the 7th power over 7 factorial plus theta to the 9th over 9 factorial minus theta to the 11th over 11th factorial, right? All that stuff. Again, this is beyond the scope of what we do here, but I'm just showing you, this is, I think, second semester calculus. You learn how to actually generate this using just the graph of y equals sine x. Okay. The reason that the small angle approximation worked, which is why I'm bringing this up, why it works, we can see it graphically here, but we can see it with the Taylor series expansion of sine x by noting that when theta is small, I mean a number smaller than 1, when theta is small, when you cube a number smaller than 1, what happens to it? It gets even smaller, a lot smaller. And then you divide it by a number, and it gets even smaller. So when you compare what this is to what that is, it's a much smaller number until theta starts getting pretty big, right? This guy, even smaller. Theta to the 5th power is exceedingly tiny. And then you divide it by 5 factorial. Factorials tend to become very large, right? 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120, right? So you're taking a very tiny number, dividing it by 120, it becomes real small. And then once you get to the 4th or 5th term, it's essentially inconsequential. You don't even need to worry about it at all, even for larger angles. Okay, so that's why the small angle approximation works. I like pointing this out because when I was hit with infinite series, you do infinite series, right? In calculus? In pre-calc? Do you do in pre-calc?
You do in calculus, but we're like not there yet.
Okay. Well, you'll see something like that. Maybe not this complex, but you won't do Taylor series, but you'll do infinite series. But this is I don't know, for me, it was hard, but that's when I was like, oh, math is cool. Like pure theoretical math, it's pretty cool. Pretty interesting. And each time you add this term, you're taking the graph of y equals x or y equals theta, and you're starting to curve it. And each iterative term that you add starts making this green line start to match that blue line. And the more terms you have, the more closely it matches. It's really cool. Really cool stuff. Anyway. Bottom line, long story short, this equation only works for angles less than about 15 degrees. Okay? That's all you got to really know. But it is in the learning objectives for AP Physics 1 that you understand the small angle approximation when it can be applied. It can be applied when theta is about less than 15 degrees. I don't know how many radians that is. It's a small fraction of a radian. But the sine of the angle is equal to the angle itself in radians. And I do 0.02, right? I do the sine of 0.02. I get okay, never mind. Oh, I'm in degrees, that's why. See? Doesn't work when you're in degrees. Radians, 0.02, the sine of it, 0.019998667. Right. So they're essentially the same number. Cool beans? Cool beans. All right. So that's some insight into the equation, the only new equation for this unit for pendulums, the period of a pendulum. So let's look at your notes that you got last week. If you don't have it, it's fine. I'll just work through this problem. But it's the problem on the last page, example 2, that has a pendulum. And we're just going to work through that problem as an example. And then you do have a new quest assignment that you can get started on. All right. A simple pendulum consists of a bob of mass 1.5 kilos. That's my mass. Attached to a string of length 1.25 meters. The pendulum is held at an angle of 15 degrees, therefore we can use the small angle approximation, and the equation for the period of a pendulum is valid. So theta is going to be 15 degrees. From the vertical, by a light horizontal string attached to the wall as shown below. So I'm going to go ahead and make my drawing. Okay. On the figure below, draw a free body diagram showing and labeling the forces on the bob in the position shown above. The lengths of the arrows should be consistent with the relative magnitudes of the forces. So for part A, here's my pendulum bob. Got to draw essentially a free body diagram. So what forces are acting on this pendulum bob when it's sitting right here?
Force of gravity.
Force of gravity. mg. Note it says the lengths of the arrows should be consistent with the relative magnitudes of the forces. Notice it doesn't say exact, right? It just says pretty consistent. There are ways of losing points if you don't draw the arrows the right length, the proper length. So what other forces do I got?
Force of tension.
How many?
Two.
Two. I got two. So let's call the one that points up to the left, and I'll explain why I'm doing it this length. I'm going to draw that about that long. I'm going to call that FT1. And then this one I'll call FT2. And that I wouldn't lose any points for drawing the magnitude, the relative magnitude is fine. Notice if I took mg and I lined it up to the tip of this one, and I took FT2 and put it there, I get a triangle, right? And the last arrow points directly towards the tail of the first arrow. When we do our decomposition, though, it'll be a little more obvious. Okay, so that's number A. Part B says calculate the tension in the horizontal string. So for part B, we're looking for FT2. Now, if you're like me, you're probably using your standard coordinate axes, where to the right's positive x, up's positive y, because I know that FT2 and mg align with those axes, so I only need to worry about FT1. But what should I probably do before I go on to figure out what this is?
Decompose FT1.
Probably decompose FT1 because it does not align with my coordinate axes. So I need to decompose FT1, but I need to be careful here. Some students get locked into the horizontal component always being the cosine component, the vertical component always being the sine component. That's not the case here because what angle in this triangle do I know? I know that top angle, right? This is theta. That angle is congruent to that angle. Right? If I was to draw my tension here, then that angle is congruent to the angle that I make whenever I decompose that vector. Making this the opposite side component or the sine component. So this is FT1 sine theta. This is FT1 cosine theta, because that's the adjacent side. All right, well, I got my free body diagram decomposed now. I know that FT2 has to equal FT1 sine theta, right? Otherwise, it would be accelerating in the horizontal direction, which obviously it's not doing. So I can just write that equation. That's essentially applying Newton's laws of motion, right? Newton's first law specifically where you have zero acceleration. So FT2 is simply going to be FT1 times the sine of the angle theta. But that presents me with a problem. What's my problem? We don't know FT1, right? Yeah. All right, well, I have one equation, but two unknowns. But I've only dealt with one direction in my coordinate system, so now I look at the vertical direction. Right? And then I see that ft1 cosine theta equals mg. Right? This vector has to equal that vector, otherwise the object would be accelerating in the vertical direction. Note that we are firmly in the realm now where when we see FRQs, chances are you're going to see previous units, concepts from previous units incorporated in the FRQ. And this one you'll see there's quite a few actually. So now we're doing Newton's laws. We're doing force analysis, Newton's laws. So yes, I have one equation here, but I can write another equation by equating ft1 cosine theta with mg. And then I can solve this for ft1 and then just plug in my result here. So here I just divide both sides by cosine of the angle theta. And I get that ft1, the actual expression for the actual tension is the weight mg divided by the cosine of the angle. Which I can then take and plug in for ft1 over here. When I do that, I get ft2 is going to equal, instead of ft1, I put mg over cosine theta times sine theta. And you can just plug in your values now, or if you're in pre-cal, you know that mg over cosine theta times sine theta I can also write as... What? Someone said it. Tangent. Here I got sine theta in the numerator, cosine theta in the denominator. Sine theta over cosine theta is tangent theta. Sine adjacent, opposite over hypotenuse, over adjacent over hypotenuse is opposite over adjacent. So I can write that as mg tangent of theta. Now you don't need to do that. Right? You can plug it in the values here and you're just fine, but you can write it a little more succinctly as writing mg tangent theta. Physics is now done. The rest is just arithmetic. We just plug in mass 1.5.
Oh wait, didn't we have the length of ft1? Isn't that what L is?
That's the length. That's not the tension.
Oh.
Ft1 is the tension, the actual tension within the string. So ft2 is equal to mg times the tangent of theta. Or again, if you're not in pre-cal or calculus, then it's just mg over cosine theta times sine theta. So m is 1.5 times g, 9.8, times the tangent of 15 degrees. Make sure you're in degree mode if you're in calculus or pre-calculus. 3.94, that's what I got when I did it in my head.
Oh, very cool.
3.94 newtons. So nothing about simple harmonic motion here. It's all forces. Yes, ma'am.
Just a quick question about like the formality of FIQs. So you know how we did our free body diagram on A, and then we went to B, and then we realized we had to break down FT1. We did it back on A. Would they count off from that?
That's it. Historically, they have. Okay. Historically, they have. And so, yeah, you probably want to draw a new sketch for your free body diagram. In the last few years, they've been getting away from that, but they haven't been explicit about it because it's the College Board, and who knows what they're thinking.
But it would be safe to just draw them.
It would be safe. Thank you for bringing that up. I should bring that up. Yeah, it would be safe. If you have a free body diagram as an answer, like we do in Part A, you just want to leave it at that. Okay. And then going on to the next part, if you need to decompose anything on that, just do another quick sketch of that on your other part. Because a true free body diagram only indicates actual forces. Components aren't actual forces. Components we use to make our lives easier, but they don't represent actual forces. They represent forces that, were they to exist, would be equivalent to the force that actually exists. So that's an excellent point. Thank you so much.
Which is so weird because if you have those on a free body diagram, you show your knowledge that that exists. Yeah. Whatever.
I think there's been so much pushback that they've actually started being a little more lenient on that. Yeah. But who knows? To be on the safe side, since you never get to see your exam, thank you for bringing that up, Alex. I appreciate it. Okay. So that was part B, right? Yeah. So part C, the horizontal string is now cut close to the bob and the pendulum swings down. Calculate the speed of the bob at its lowest position. All right. So it starts over here. String is cut, and so it swings down, and let's say it swings down to here, at which point it's grown somehow, and at which point it'll have some velocity v. That's what we're looking for. So I'll say VB for V bottom. Now we can't use Newton's laws here, or we can't use Newton's laws and combine them with kinematics because the acceleration will not be constant. The acceleration of the object will change as it arcs downward. What can we use to figure out the velocity? Can't use kinematics. The acceleration is changing. You can't use kinematics unless you have constant acceleration. Now you're talking circular motion, right?
Yeah. Would that count?
No, that acceleration will only, because remember when we use circular motion, vertical circular motion, we only deal with what's happening at the bottom and the very top, maybe on the sides. But as the object moves, the centripetal acceleration will change for a vertical circle. It's not going to be uniform accelerated motion. So just like we can't use the kinematic equations, we can't use the uniformly accelerated motion for the entire motion.
Why can't you use Newton's laws?
You can use Newton's laws, but it's going to be a lot more complicated because the acceleration is constantly changing. So you're going to have to use the calculus version of Newton's laws if you want to go about it that way. There's a much easier way.
We can use mechanical energy.
You can use conservation of mechanical energy. Yeah. An object's going to be moving it's going to be changing elevation and changing velocity simultaneously. So as the object swings down, it's going to take its gravitational potential energy and convert it to kinetic energy. Right. All right. It's still tricky, though. This is still tricky. We've gone over a problem like this before, but this is a good opportunity to re-emphasize some stuff. So we are going to use the conservation of mechanical energy. So initial mechanical energy equals final mechanical energy. Initial mechanical energy is all potential, right? It's all potential because the string is cut, and so at that instant the object is not moving. So it's all gravitational potential. You can write plus the initial kinetic, but we know that the initial kinetic is going to be 0. And then that's going to equal the final gravitational potential plus the final kinetic. Well, at the bottom of the swing, that's a very convenient place to define the gravitational potential energy to be 0. It is arbitrary, so we are free to do that. And then the initial gravitational potential energy, it's mg times the initial height, I'll call it y naught. And that's going to be equal to 1/2 mv at the bottom squared. That's the equation for kinetic energy. Everyone brought mass to the party. And then I can just multiply both sides by 2. And so I get 2 times gy naught equals the velocity at the bottom squared. Then I just square root both sides. And I get that, bring it up here, the velocity at the bottom will be the square root of 2g times that initial height. But I do have a problem here.
You don't know the initial height.
I don't know the initial height. Now we have done one like this before, and I pointed out this kind of a problem tends to trip students up in introductory physics. We don't know the height, but we do have enough information to figure out what it is. So let me just label it real quick. I got initial height, y naught. Does anyone have a method by which we could do that?
I'm sure that the length is 1.25.
I know the length is 1.25. So that's essentially this distance. And that's essentially this distance.
So you know the final one.
And then I can make a right triangle here. And just call, actually let me write this out here. This whole distance is the length of the pendulum. But if I can figure out this distance, I'm just going to call it, let's just call it x. It's an unknown. If I can figure out what this distance is, I just subtract it from the total length, and I get the initial height, right? Well, how can I do that? Well, I can relate things I know, like this angle and that length, to this side using this guy's adjacent to the angle. This is the hypotenuse,
Yes, I'm
which is adjacent over hypotenuse. So tell, guys. Cosine. Thank you. Cosine. Cosine of the angle is the adjacent, which I just called x. You can call it whatever you want, over the length L. Multiply both sides by L, and I get that distance, x, is L cosine theta. Well, if this is L cosine theta, this distance here, and I subtract it from just L, then I should end up with that initial height. And so my initial height, y naught, is simply L minus L cosine theta. A lot of students memorize that. This is a situation that you end up encountering somewhat often, very often when you're dealing with pendulums. Not very often, but it does pop up from time to time. You can obviously factor out an L, so you get L times 1 minus cosine theta. Now I have an expression that I can put in for y naught up here. So now I know the velocity at the bottom is going to be the square root of 2g. Now if you're going to do L minus L cosine theta, you better put it in parentheses when you multiply it by 2g. That's why this is a slightly less error-prone way of writing y naught, because then you can just write L times 1 minus cosine theta. And we should all be able to do that in our head. Square root of 2 times 9.8 times 1.25 times 1 minus cosine 15. What is that, Kurt?
Oh, you 0.91.
What?
Is that Kurt? No. I have not put it all in the category. Oh no.
For shame.
I have 0.9136 or 37.
I got the white. They fit it to the
Well, I got something very different. Hold on. Oh, I'm in radians. Dang it.
Are you in radians?
I got 0.9136.
That's what you got, right?
0.9138.
0.9134.
Oh.
Means we're saying.
Yeah.
3 digits is fine. All right.
They wouldn't count off, right?
So, any questions about that? That's tough. That's tough to figure out. This is the second or third time that I've actually done a problem where we had to use this to analyze a triangle in this way. It does pop up when you do energy, but there are other cases, not so much in this class, where you actually see this kind of thing. So just be ready for it.
I do have a presentation question.
Yeah.
For the FRQ. So part of the points is writing and labeling, or at least writing your equations, right?
Yeah.
So do you need to show how you found why not, or can you just pull why not?
You won't need to. No.
You won't need to.
No. If you would have to write an equation, when we did our FRQ grading, you saw the student wrote an equation that represented the conservation of energy, right?
So you would get points for writing, at least writing.
Yeah. And then you might get 1 point for showing that y naught is equal to L minus L cosine theta. So as long as you write y naught equals L minus L cosine theta, or with whatever symbols you're using, then you're fine.
But if you had just inputted it into your equation without showing the actual relation.
That's where it's a little iffy.
Anything that is just numbers, plugging in numbers, you never really have to write it down, right? But anything that's
Right.
like theoretical, the variable.
Yeah.
Probably.
Now I would give, if I was grading that, I would give the point to him
Because they still substitute.
because they've shown that they know that the height is given by that expression because they put it in the equation. I just can't guarantee it because I'm not going to be the one grading your AP exams. Okay. Calculate the tension in the string when the bob is at its lowest position. Please understand we're not going to finish today. We're going to have to wrap this up tomorrow. When it's at its lowest position, I'm actually going to bring this over to here. And again, it's not quite obvious what we're going to have to use in order to calculate when the bob is at the lowest position with the speed that we just calculated. Sorry, I shouldn't. At the lowest position where it's moving at the speed we just calculated. So let me write that right here. So it's moving with sun speed v at the bottom. It says, what's the tension in the string? Well, if I don't know where to start here, if you're asked to find forces, a good starting point anytime you're asked to find forces is by doing what? Starts with an F. What? Well, you always want to do something else before you use Newton's laws. Starts with free body diagram.
Yeah.
So let me ask you this. Is this, if I draw mg and the tension force the same size, is that a valid free body diagram for this situation? No. If it was, then the pendulum would get to the bottom and then it would move in a straight line at constant speed. Because that would imply that the net force is 0. And in the absence of a net force, objects move in a straight line at constant speed. So which of these must be bigger? If it's in a circular, semicircular arc.
The tension force has to be bigger.
The tension force has to be bigger. Tension force has to be bigger because it's moving in a circular arc, and the net force always points in what direction when an object is moving in a circular arc? Towards the center. And so, yes, the net force will be smaller than the tension because it's being offset by mg a little bit, but the net force must point up. So if I was to draw the net force vector here, it would be like maybe about that big. That's the net force vector. Then, after I draw my free body diagram, now I can apply Newton's second law and say the net force is mass times acceleration. But right here at the bottom, I know that the net force does point exactly towards the center of the circle. So I know that the net force is centripetal. I know the acceleration is centripetal. And we'll pick up here tomorrow. There is a quest assignment that is due Wednesday night. We'll work on it in class tomorrow. Those at home, get started on it. Do a problem or two for online attendance. See you tomorrow.